Webinar is now broadcasting. All right.
Okay, I'll kind of start right now. It's 11 o'clock. We've got a lot of participants that are starting to join already. I've got about 78. That's about half of the people that are signed up. So we're going to let the participants keep logging on here for just a couple of minutes, and then we're going to get started with today's seminar. So first of all, for those that are on already, thank you very much. Really appreciate you joining us for part 2 of our four-part series on multi-stack, advanced chillers, and chiller design. So we'll kind of stop here for just a second and let a few more get on. Like I said, we've got about a little more than half of them that have signed on. So usually it takes a couple minutes for everyone to join. So thank you for spending your time with us today. Well, just to let you know, we've got about 100 people that are joining so far. We have about 150 that have signed up. So we're going to wait a few more minutes just to make sure we get everybody on. And we'll start about 3 minutes after the hour. Today's topic on the second phase of our 4-part series on chillers, advanced chillers, and chiller design are trends in electrification. So I don't know how Bruce managed to do this, but it's probably one of the more timely discussions based on this cold weather snap of in the Midwest. But I think it's certainly an exciting topic. It's a topic that is here to stay. And regardless of all the interesting things that are happening with electricity in the last week, we know that there's a lot of exciting products that can help support the desire to support electrification. So just a couple of housekeeping things here. This is the second part in a 4-part series. The next 2 will be Thursday at 11 o'clock on February 25th and March the 4th at 11 o'clock Central Standard Times. We are recording this, so we're going to hold all the questions until the end, but you may use the Q&A feature down low on your Zoom in order to ask questions, which we will address at the end. Obviously, there's a chat function as well, and if you want to jump in with anything, we appreciate any comments that you have. The first segment of this was pre-recorded, and it can be found on the AES website, which is aeskc.com, and then just hit the training button, and then you can view the first one if you missed it. We'll be posting all the other ones there as well. If you do register and attend all 4 seminars, you will be entered in a drawing for a Traeger grill. So we'll be giving away 1 Traeger grill at the end of the group of seminars. All you need to do is we do ask that you fill out the short survey at the end. That way, that's how you'll get entered. If for some reason you aren't able to stay on, we will be emailing the survey out to you. And so that works as well. If your company has a policy about not being able to receive gifts, there's an opt-out option in the survey. And then there's a place to click to get PDH credit and a copy of the presentation. So let's go ahead and get started. Today we have our guest speaker, Bruce Barrett. He's a regional sales manager at Multistack. And Bruce, I'm going to turn it over to you.
All right, thanks, Keith. We'll try to keep it again to about 40 minutes for the presentation today. Again, talking about heat recovery and trends in electrification. We're going to talk about different products, different strategies. Really some opportunity out there for changing the way we think about making hot water in our buildings, saving some energy. I do have to show this slide just to underscore Keith's drive to give away this Traeger grill. I really enjoy my pellet smoker. It's not a Traeger, but it's a good one too. Pretty soon we'll be cooking outside. Electrification, it really is here already. Some of the more progressive communities are banning the use of fossil fuels altogether. DC, Berkeley, Washington, DC, 8 states, including Puerto Rico, are investigating going carbon neutral by certain dates. California, Berkeley, working on a lot of different equipment configurations out there. There's no natural gas on site. Granted, there's some great weather too, which requires some very low heating temperatures. But it's upon us. There really is no debate about it getting started. It's already here. ASHRAE has already done numerous conferences and expos. They did have to cancel the one this year, but last year in 2020, they did have a discussion about how they're going to shape the future potentially of many different areas of the world via electrification. So the 4 topics we're going to talk about today are employing some recent or new developments in technology, some old technologies that are trustworthy, tried and true, and they work very well, like geothermal, applying magnetic bearing chiller technology, making hot water using the mag bearing product, and then advancements in air-to-water heat pumps and how they have evolved to deliver both warmer temperatures and extract heat, additive compression with new compressor technology at very cold ambience. So just quick definitions. You know, when we're making hot water with a chiller, basically we're using the heat of compression. When that compressor operates, when it compresses that fluid, it creates heat. We're able to calculate that heat rejection plus some energy that we've extracted from the chilled water side. So we're adding the heat of compression to the extracted heat, getting our total heat of rejection. A lot of the times you can just drive down the road and see this every day on a cold day in Kansas City. If you're driving down the road and you see the cooling towers rejecting heat and it's 25 degrees outside, you know the boilers are running. That's really wasted heat coming out of that cooling tower. In the HVAC world, you know, when I'm driving down the road, I see this all the time. I think of money going out of the tower. Some basic facts, you know, there's a COP, or the calculation of performance or efficiency of a boiler. They can range anywhere from 60 to 95%. All boilers are always less than a 1 COP. And in the heat recovery world, we're using extracted heat and the heat of compression. We can get COPs greater than 7 times greater than what your best boiler on the planet can do. Some great jobs we've done here at Multistack, employing the use of heat that's already on the campus. University of Iowa, a very cold climate. They built an indoor football practice facility. They were going to bring boiler plant piping almost a mile to this facility to do the underfloor heat. The engineer explored some different options. They had a chilled water return main on the campus, a big 60-inch pipe that was always full of 50, 55 degree water. We're extracting heat out of that pipe, dumping it back into the return to the campus, kind of a quasi geothermal application, but they saved well over $1 million in boiler plant piping. They're using chillers to both heat the underfloor system as well as do domestic hot water heat for all their showers, for all the football players' showers, their therapy tanks, etc. So 66% better efficiency than the 2007 baseline. Got a huge rebate. Very successful job for us. Good creative use of energy they already had on their site. Now this is a biggie. This is frankly changes in code, building code. The new 90.1 standard does have it written in that 7% of the available simultaneous heat must be recovered on buildings that have beds, hospital beds, 300 tons and greater. So if you do the math, that's a great application for a 300-ton job to have a very small heat recovery system and comply with that standard of 90.1. Well, how would that look in a hospital? Well, we've got a boiler creating heat, adding it to the building, maybe to the perimeter of the building, maybe some of the core. We've got a chiller that is removing heat from the building, but also disposing that heat via a cooling tower. We'd like to close that loop. Instead of adding dollars to the boiler, adding money, energy to the boiler, and also throwing heat out of the tower, we want to reclaim that. We don't want to throw it away. And this is how it looks, some very simple piping. We take some return water going back to the chiller, and we pass it through a heat recovery chiller side stream series application. We create chilled water and we mix it back to the main chiller plant. We're extracting heat out of that chilled water return pipe. We're adding the heat of compression. We're doing the same piping on the return back to the boiler. We're intercepting some of that, taking some of that water. We're adding the heat that we just pulled out of the chilled water side. We're adding the heat of compression. We're elevating that. We're mixing water back to the boiler. We're unloading the boiler, saving a lot of BTUs. Again, COPs of certainly greater than 3, but all the way up to 7. Now I've put 90 and 120 degree hot water. We can do all the way up to 140 degree hot water with a water-to-water heat recovery chiller. So 2 pumps, 4 pipes, very easy installation to do heat recovery and comply with that 90.1 standard on hospitals. Do have to talk a minute about modular chillers and why they offer a differentiator to a single machine, a screw or a centrifugal that has a single bundle. We've got multiple independent refrigerant circuits piped in parallel. We've got a common master controller controlling each one of those. Each one of those modules can be isolated electrically and hydronically. We can unload to very low levels. If you need low amounts of reheat, we can deliver that quality of hot water without sacrificing kW per ton. A large shell and tube machine cannot unload very well and deliver that quantity and quality. Also save some pump energy. If you've got a larger array, we can unload to single modules. So excellent use of a modular machine to do heat recovery, both on the performance side, the energy side, and the temperature side for quality of temp. Technologies, some new technologies, new 3.5 year old technology that we've been employing is on scroll heat recovery chillers is true variable speed compressors. It is a matched engineered drive and compressor. They can load very well, about 30% in a heat recovery environment. They can be overdriven, so they can get some extra capacity. You do have to mount that drive somewhere on the equipment, but it does give better part load performance throughout the operating range as opposed to on-off compressors. They can be single or tandem. You can just put one of those compressors to be your first on, last off. And again, achieve better temperature control on a heat recovery chiller using a true variable speed compressor. There's also some bonuses there. Motor efficiency, out of the box, never worse than 92% motor efficiency versus an on-off compressor. Inrush, you can really lower your electrical wiring costs and improve your inrush on your total system performance. This is a little bit of an eye chart. It's actually a 10-ton fixed on top versus a larger 12-ton true variable speed on the bottom. and upwards of 70% inrush savings just by going to that variable speed compressor. Great power factor out of the box, always going to be greater than 0.90. A lot of government facilities require 0.90 power factor or better. You can get that with the true variable speed and some good harmonic suppression. It's about 40–50% suppression out of the box with a standard drive. Again, a little bit more of an eye chart, but what I'm comparing here is a 50-ton module at various temperatures. And I'm going to talk a little bit more about the temperature, how high it is as compared to the COP. So I ran some different scenarios here for a 50-ton module using on-off compressors at different temperatures. The 90 to 120 degree hot water temperature has a very, very high COP, 7.4 combined COP. If we look at 100 degree hot water, it goes all the way up to 9.76 heating COP. Just want to point out that if you lower your hot water temperatures, you improve your COP. With true variable speed, you get a small percentage improvement, not only at full load, but at part load conditions. Again, it's a PM motor, so it's going to have better motor performance out of the box. 7.56, making 120 degree hot water and about 44 tons. So I took it one step further in my analysis. I know a lot of people get nervous talking about lowering hot water temperatures and what that means for quality of comfort in the building. And I don't want to pick on Texas too much. They're in a heck of a mess right now, but they have operating temperatures on their coils 160, 170, 180. You have some benefits there that you have very small coils, but you're also hurting your COP performance on the heating side. So again, I configured some coils at different temperatures and looked at the airside pressure drop and the cost added to that coil. So doing 140 degree hot water, a 2-row coil, a 0.23 pressure drop, making 120 degree hot water, it's about a 6% add and a very minimal airside pressure drop change. Now we've got to go all the way down to 105 degree hot water to add a 26% add. But even on a coil, adding 26% to a coil is not that large of a dollar add per se. And the COP benefit that you get, I'm not telling you what temperature to design your heating system, but I think it's valuable to look at that temperature and the impact across the board. It appears to be very minimal, driving towards about 120 degree hot water with your coil cost and your airside pressure drop. Again, all of these coil selections were 862 MBH. You can heat with 100 degree hot water. You just need a 4-row coil and you suffer some pressure drop loss through your coil and some fan kW. Again, just a quick summary. Matching your simultaneous load is very easy with a modular chiller. It's a simple configuration, 2 pumps, 4 pipes, and a very, very small footprint. You can get the quality of temperature that you need across different loads without sacrificing your kW per ton making hot water. All right, so that same heat recovery concept is employed for centralized geothermal heater chillers. We're simply using the heat of compression when we have the opportunity to do simultaneous heating and cooling. When we employ the variable speed compressors like we did in this job, Lincoln Electric service, it's in my background, very nice job. One has to think, why did the electric cooperative pick variable speed compressors? Well, they understood the low inrush, the great power factor. They're the utility company. They want to keep inrush low. And they wanted to leverage simultaneous heating and cooling in a geothermal environment. The added bonuses here, very low refrigerant charge. Very quiet chiller. This mechanical room is large, but it's also very, very quiet. Really a great job for us. And we're controlling within a ½ degree on the heating and cooling side for this job. If you ever get over to Lincoln, he's very proud to show off his facility. We're proud of it as well. It was the very first geothermal heater chiller we did with true variable speed compressors. Geothermal, it's still the most efficient HVAC heating and cooling battery that we have. It's easily adaptable. In the Midwest, we've got a bounty of good aquifers underneath us. The Dakotas is spectacular. Iowa's is really good as well, but it's still the most efficient heating and cooling HVAC platform that I'm aware of. How does this fit electrification? Well, private owners and local governments are mandating carbon emissions reductions. Carleton College in Minnesota, a great example. Their benefactors, their donators of the college are making the rules. They have the gold. And they've instituted some very aggressive goals for their campus. And one is to be carbon-free by 2050. They're instituting solar, photovoltaic cells all over the place, big farms, as well as wind. They're not off gas just yet. They've got 2030 goals as well, but 2050, I'm seeing a lot of colleges, universities, because of the people that have the money, are making those rules. This is our 850-ton geothermal chiller that we've got on campus. We're doing about 50% of their total cooling capacity. They still have another centrifugal plant, so it's a hybrid plant. We're simply tying into that master loop and providing, we're the first on chiller because we're the most efficient, better than the current centrifugal. So we're first on, runs as many hours as we possibly can, providing right now about 50% of the campus heating as well. Now, I mentioned centralized geothermal. Many of you are probably familiar with distributed heat pump systems, where each room or section of a building might have a heat pump up in the ceiling or in a wall casing. Each one of those distributed systems have reversing valves, so they're either cooling or heating. With a centralized system, we could have a reheat system with a cooling coil and a heating coil. We can leverage that simultaneous benefit, and we're also offering a lot of redundancy. If a distributed heat pump system goes down, you lose that section of the building. You're not able to do any reheat dedicated in that building. Centralized, you've got a mechanical room, you've got redundancy built in, and you can do reheat capabilities. I mentioned screws or centrifugals. They make double bundle heat recovery chillers still to this day. They're very large. They typically do not have VFDs, so you don't get that low inrush benefit. As they unload, they typically get worse in kW per ton. They demand large flow rates, larger minimum flow rates than modular machines. They're big. They can be very loud and a lot of vibration. The picture I show up on top was in one of the buildings next to the Capitol in Wichita. 16-inch base, steel bases, spring isolators, and every time it turned over, they'd have to pay peak rates with those large compressors. Also, it's lots and lots of oil to maintain that system, which degrades over time. That was last week's magnetic bearing discussion. I'll talk a little bit more about bank bearings, but all of those oil centrifugals and oil screws will degrade in performance over time as well. So last week we did talk about our TTH, or our high lift magnetic bearing chillers, and how they were employed in air-cooled chillers with very high ambience. Texas, Oklahoma, Phoenix, Arizona. We use that high lift compressor anytime we get around 110 ambient. Why? Because that compressor has a very high pressure ratio. It can have very hot discharge temperatures to the condenser side. It's still very compact and lightweight. So the next progression is carrying this compressor towards heat recovery chillers in a modular format or in a common shell and tube flooded machine, if you will. Still has the soft start, very low inrush, exceptionally quiet operation. And again, no oil to degrade performance over time. So the machine on the upper right, we're just taking that high lift compressor and we put it on a set of shells. So if you've got a large enough load for 100 to 1,000 tons, we can employ this chiller on a water-to-water heat recovery application, or again, with the high lift air-cooled machines. Because we have approximately 100 tons per compressor, we can unload to that one compressor operation and still maintain the temperature leaving that machine versus a single compressor or dual compressor machine that cannot unload very, very well. This Foss turbocore compressor is offered in 134A, 513A with a click of a button in our selection program. And we're also offering through special engineering 1234ZE for near zero GWP refrigerant offerings. So just giving a quick example, 500-ton cooling load with 6 cents a kWh, which is about the rate, 80 cents per therm, 90% efficiency boiler running 4,000 hours. It's about a 3 to 6 year installed cost payback employing the mag bearing technology. Large reductions in carbon emissions, 328,000 pounds. There are some carbon offsets that some utilities are giving as a bonus. It's about $30 a ton, so $4,900 carbon offset if there's carbon penalties, if you will. Some look at it as bonuses, some look at it as penalties. So really the eye opener is a 3 to 6 year installed cost payback with those other bonuses. Very small chart, I apologize, make your eyes sore. This is an actual job where we had 38-degree leaving water on the chilled water side, 135-degree hot water. We can go up to about 150, 155-degree hot water with this high lift mag bearing machine. The kW per ton column, 1, 2, 3, 4, 5, 6 rows over. If you look at the kW per ton, as that machine unloads from 100 to 10%, it doesn't change very much. If you look at a centrifugal or screw, you're going to notice that kW per ton stops. It won't run at about 50, 60% load. And at 70 and 80% load, the kW per ton gets worse. It goes up. So employing multiple compressors across this machine gives you that aforementioned bonus of very smooth kW per ton and great unloading all the way down to 10% in this application. All right, on to a different technology, some packaged equipment. We've got a air-cooled chiller that can make hot water. We're employing on-off compressors at the moment. There are no variable speed compressor options on the market for this machine. One big reason why is we have 3 heat exchangers. We've got an evaporator, we've got a condenser, both braze plate, and we have the coils. That's our 3rd heat exchanger. We do them in 20, 30, and 60-ton modules. They're modular, so you can put multiple machines together. You can pair these with just cooling-only machines. You don't need the entire array. You can figure out your building loads, your simultaneous need, and just use one of these ARA modules to do your max simultaneous load. You've got that built-in redundancy across the same modular concept. We're getting great COPs in that simultaneous mode, better than 5, really depends on the temperature and glycol percent. I do want to point out that we can make, say, 120, 125 degree water, all the way up to 130, again, depends on glycol percentage, etc., all the way down to about 40 degrees Fahrenheit. In other words, we can only extract so much heat back through the coil from the air, add a heat of compression, and make that quality of water. Okay, so that's one of the drawbacks. But by far, this on the coasts and certain municipalities that are requiring it, or customers that don't have any gas on their job site, this is the #1 machine that they're applying in that market right now. All right, let's look at the 3 modes. Important to understand these. All right, so we've got 3 different modes. Cooling mode, it's operating identically to an air-cooled chiller. We're extracting heat from our evaporator side. We're discharging that heat to the coil. Simple. The second mode, heating mode, it's an air source heat pump. We're extracting heat from the air, again, down to about 40-degree ambient, and we're adding the heat of compression to make hot water out of our condenser braze plate heat exchanger. The air is our heat source, and we're adding heat of compression. Third mode, really not using the coil. We're using it as a water-to-water heat pump that we've talked about earlier. It's 4 pipes, 2 pumps. We're not using the coil at all. It is a strict water-to-water heat recovery chiller. Pretty simple concept. Our controller takes over 4 valves to direct where refrigerant is going. There's ball valves in there, so it positively isolates refrigerant going to the coil in this instance. All right, future development. This is where I believe things are going to really take off because of the limitations of the current compressor technology being about 40 ambient. Now, we can make hot water below 40 ambient, but it often needs a reset schedule to reset your hot water quality. Okay, people don't like that very much. The new technology is using refrigerant injected compressors, which expands the operational envelope all the way down to 0. We can heat up to about 140-degree hot water on the high end, again, depending on glycol percentage, etc. 15-ton compressor is the only technology that's being shared right now with manufacturers such as us. So a 30-ton module is our limit. There are no alternative refrigerants in play yet, but there is chatter of the development of that. Typical development from the compressor manufacturers is 2 to 3 years. That's just a guess at the moment, hoping they speed this up. We are getting prototype compressors right now for the refrigerant injection that we're employing in our equipment. We want to make sure it works, it gets tested. We'll have a beta site and make sure it works. So I don't know, realistically speaking, maybe a year, year and a half before we go full go with refrigerant injection. To do heating only for any type of this technology, it requires glycol. I'm going to go back 1 slide. When we have a heat source, the air, and we're adding heat of compression, there's dormant refrigerant in the evaporator on the right side of the screen. When you have dormant refrigerant in there and water that isn't moving, you're going to freeze pipes. So we require heating only machines to have glycol on both sides of the machine. Dormant heat exchangers have refrigerant trapped in them. And that's the reason why we require glycol. There still is going to be reset schedules involved as we travel down to near 0 ambient. There is also a defrost cycle. You can frost your coil. You need to warm it up. So you need redundant modules to carry the load while you're doing defrost in that dormant thawing out cycle for the module. That's where the modular design comes into play. You can plan for that defrost cycle by adding a redundant module. How does it look? Well, the compressor simply has a port in the side, like an interstage economizer. It takes mid-pressure gas and re-injects it into the compressor so it can keep spinning and pushing the heat of compression up. Increases the refrigerant flow by about 20%, but it greatly extends the operating range in those colder climates. Again, an eye chart, but the green line is our ARA 60L. On the bottom is ambient. On the left is the temperature of hot water. So you can see somewhat our reset schedule with the on-off technology. Once we get to about 30-degree ambient, I start losing the quality of water. The big line, the most important line, is the blue line up top, which is the refrigerant injection scroll. We call the ARA 30L. I can go all the way down to zero. It greatly expands the operating envelope. 145-degree hot water is the absolute max under ideal conditions. But again, if I go back to the study of performance, COP, how it impacts our coil sizing and our pressure drop, we can stay within a safe operational map easily around 120, even 130-degree hot water. We want to stay away from the edges. We want that machine to work. Just another example showing the refrigerant line piping and how it controls that injection process. The compressor that we've chosen for R&D development, I highlighted in yellow a little bit. It has a pre-assembled liquid injection line right in the compressor. It's easy for us to do, manufacture, install, etc. It's all pre-wired. The compressor is monitoring its own discharge temperatures. It's got sensors all over the place on it. But it's really how to, Keith, I know you're a car guy. It's a turbocharger. We're just, we're not putting nitro in it, but we're putting liquid refrigerant in it to give it the gas it needs to do that heat of compression. All right, so just a quick summary. Not only does ASHRAE require it for hospitals, but it makes really good sense to use heat recovery, to apply it in different applications. It's a great way to save energy over the best boiler that you have out there. Continue to look at opportunities to move your temperatures down, move your COP up. Look for geothermal opportunities, employing the heat recovery concepts. Centralized geothermal versus reversing valve heat pumps that are difficult to do heat recovery. There's no heat recovery option. Looking at mag bearing opportunities on maybe larger facilities with larger needs, and how well that technology without oil sustains performance over time, has excellent unloading properties without sacrificing load at low points. Air to water technology. I had a spelling there, air to water heat pumps. Should be heat pumps. The new ARA, it's gaining so much traction with this new refrigerant injection technology. It's going to expand the operating envelope. Very excited about employing that. Geothermal, still number one in my book. There's not much we can say when a private entity, the owner, makes the rules. And a great way to get there is to employ creative use of geothermal, mag bearing technologies, and those air to water heat pumps. So with that, I'll conclude my presentation and open to any questions.
Yeah, great. Excellent presentation, Bruce. Thank you very much. We have a couple of questions here. One from Josh Smith. Thank you, Josh. What's the approximate cost on a variable speed versus standard scroll compressor? And I think that's probably going to apply to the size, but let's just say in a 30-ton unit, is that a 10% increase for that?
Right.
Some idea here.
Yeah, it depends, but I would say roughly a 20% increase in cost. However, let's say you've got 3 modules, 2 compressors each, so 6 compressors total. You don't have to employ that variable speed compressor on all of your compressors. You can put it on half, you can put it on 1 to help you achieve tighter temperature control. It really depends what your goals are. If you're shooting for the stars to get the highest efficiency, tightest temperature control, all variable speed, that would be 20% across the board.
Excellent. Thank you. We have another question here. It says, I may have missed the explanation of this earlier in the presentation, but you showed a graphic with a chiller in between a chiller and boiler loop, and I don't understand the purpose of the middle chiller in this graphic. So can you just go back to that, and we'll just go over it briefly? I think it's really important that we address that, because this is the real heart of how we save money in heat recovery.
All right, so I would assume it's this slide.
Yep.
Okay, so we've got a boiler on the bottom left, a chiller plant on the top left, and in between is our heat recovery chiller. It's dedicated heat recovery. Its sole purpose is to supplement hot water and cold water. So a side stream series, we're taking water, returning back to that chiller, extracting the heat, adding heat of compression, and cooling the water before it gets back to our main chiller plant. The heat we've extracted, we're adding to the hot water loop. So this is the basic dedicated heat recovery chiller schematic.
Yeah, so to the person that asked the question, if you'll just click also in the survey that you'd like to have someone contact you, we could kind of explain it a little bit more. But basically what we're doing is we're offloading the chiller and offloading the boiler. And at the same time in doing that, we're not rejecting heat to the atmosphere through through a cooling tower, or rejecting the products of combustion through flue. And so it's more efficient from that standpoint. So I hope that answered the question. Got just another one here. On the ARAs, are the ARA 30L, is that available now, Bruce?
It's going to be, we've got our prototypes being built right now. We're probably going to go through a 6-month test and then send it to a beta site. I would say we're probably a year out.
Okay, awesome technology, by the way. Is there going to be a big penalty in energy efficiency with that unit? That was a follow-up question.
Penalty on energy efficiency. The cooling performance will meet 90.1 standards. It's around a 10 ER with a 14 IPLV in air-cooled speak. So it should meet codes, should meet air-cooled chiller efficiency codes. It's going to be interesting to see, because we keep ratcheting up performance requirements. It's going to be interesting to see how HRI treats this chiller, because it's more than just a chiller. It's also making hot water. And right now, heat recovery chillers are certified in accordance with AHRI standards. There is no standard for heat recovery chillers yet. So it's going to be interesting to see how they treat it, as a chiller or a heat recovery machine.
Well, for sure, this is exciting technology, Bruce. I thank you very much. We do not
There
have
was one more question. ARAs match. Oh, you answered that. Yes, ARAs match up with our standard air-cooled chillers. Yes.
And they do. And yes, so we're in good shape on that one. So anyway, guys, really great job, Bruce. Everyone, please fill out the survey. That's the way that you get registered for the Traeger grill, so that you can be cooking those chickens or steaks like Bruce showed at the beginning. Next week on Thursday at 11 o'clock will be our third part in this 4-part series. And we look forward to seeing you, and we thank you very much. Bruce, great job.
Thank you, guys. Thank you, everyone.